Okay, hi Giri and Jason and anyone else who stumbles upon this video and wants to kind of explicitly see the connection between Riemann sums and these volume integrals we've been doing. So I'm going to go to this graphic up here in a second, but first I want to talk to you about the day that we derived this, which was a really big deal. That was the fundamental theorem of calculus part 1. And it's really important to not lose sight of what this is saying. Now, you remember the day that we derived this, we expanded out a Riemann sum, and remember that was the day that everything, all the stuff in the middle canceled, right? We had cancel, 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 right? And at the end of the day, what happened was, oh my gosh, what's left is just the first and the last term. And again, if you don't know what I'm talking about, just go back and refer to your notes. That day that we derived the FTOC part 1, it was like mayhem. Remember that? And that's when I almost kicked Giri out of class because he said, this is not a big deal. And then Walter said, what are you talking about? It is a big deal. So it was like the equivalent of a calculus brawl, all right? But let's not forget really fundamentally what this is saying. What this is basically saying, after you get to the end, it's saying that whenever you're looking at, whatever this is, right? This on the left-hand side, whatever this function is, okay, the definite integral of this function involves the antiderivative. This function could be any number of things in context. It could be, it could be the number of flies. It could be the length of a radius. It could be the thickness of moss on a hillside. So what this function is, while we do say, and we call it f prime of x, it's nothing other than just a function after all. And the evaluation of whatever is here, the definite integral of some function, always involves its antiderivative. Okay, so this graphic I find to be kind of interesting. If you look what's happening here, so this is this curve right here, okay, this curve, and the revolution is about the x-axis. And now what's happened is we've divided into subintervals, and I don't think you're able to see my, my cursor, but you see how the delta x subintervals, now here they aren't all the same, but one delta x is here, it looks like. Another delta x looks to be possibly here, and then 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 here, okay? And if you want to build one of these, we can call this, I'll just choose this one right here, let's call this the kth subinterval. And now the kth subinterval, we know that in the days of the area, right, if this were an area question, the kth subinterval would be the kth rectangle. But now, in the case of this problem, where we take this area that's bounded in here, and we revolve around the x-axis, and I'm actually going to erase that because it's just hard to see. When we revolve around the x-axis, we have a volume. So really what happens is the kth subinterval really is the kth cylinder, so to speak. The kth cylinder has a certain volume, and what is that volume? Well, the kth cylinder has a volume equal to pi r squared h in general, all right? And again, now in this case, pi r squared h is this distance right here. So this is h, that's the height of the cylinder. And so the height of the cylinder is just whatever delta x is. Now remember delta x, we called this b minus a over n, right? But it's just delta x in the kth subinterval. This becomes delta x is h, and pi, of course, is pi. But the radius goes up to the curve. So the radius is whatever, this is f of x in blue up here. So this is f of x squared, right? So this is the kth subinterval's volume, because we're talking about, in this context, the kth subinterval here results in a cylindrical volume. And what we're saying here, if you look over here for a second, don't worry about this max delta x sub k here. In this drawing, notice that the delta x is not constant. just what this is saying here is if the largest delta x approaches 0, then all the delta x's approaches 0. Again, don't worry about that. But think of it this way, in our vocabulary, the vocabulary we used is if this delta x approaches 0, okay, we're adding up the summation from the first cylindrical volume to the nth cylindrical volume of pi r squared h, okay, because we're adding up from the first to the nth cylinder. Now, without this limit here, this is just a finite Riemann sum. All a Riemann sum is, Jason, Gary, all a Riemann sum is a Riemann sum is a summation that is generated from the idea of some incremental change in x delta x. The Riemann sum is just a sum in a given particular context, and the context here is a Riemann sum is a sum taken over some interval where that interval is then subdivided. Okay, but this piece of it, the summation from k equals the first cylindrical solid to the nth cylindrical solid, is pi times radius squared times delta x. Well, in this case, it just so happens that the radius squared is just a function, right? This becomes summation from k equals 1 to n of pi f of x squared delta x. Okay, now all you have to do is say, okay, well, it looks like that if I want the limit of n, or if I want delta x to approach 0, so we've written, I think, the limit as n approaches positive infinity of the summation from k equals 1 to n of pi times f of x squared delta x. Here's what I'm going to do. Watch. Ready? All I'm going to do is just say that back in the day, we had this. The limit as n approaches positive infinity of the summation from k equals 1 to n of b minus a over n times f of a plus k delta x, right? You're probably wondering to yourself, well, this is very odd. This is why I asked Ms. Yem the question, because this looks nothing like this. Okay, well, I'm going to challenge you there for a second. If you look at this picture, let's take a look at this. Do you see how in this picture it's hard to tell, but maybe they used, for example, for subinterval 1, it looks like they used the right endpoint of that subinterval as the radius. Maybe here they used, look, the right endpoint and evaluated there for that radius. The right endpoint of a subinterval evaluated at that radius. So here, what we can do here is this. Well, this radius squared, I could think of as just, f of a plus k delta x, right? All of that squared times pi, okay? Now, here's something I want to share with you. I'm going to do this. Let's just say that, f of x I called the radius, right? F of x is the radius, but really, f of x squared, right, is just going to be some other function squared. In fact, I'm just going to call it the function, I'll call it the function h, okay? So let's just call h of x just the radius squared function, or h of x is just f of x. Well then, isn't it true that if h of x, and this is perfectly fair to define a function in terms of an operation on another function, well then if that's the case, couldn't I just rewrite this whole thing, f of a plus k delta x squared? Okay, that's just the same thing as h of a plus k delta x. And then what we have is the limit as n approaches positive infinity of the summation from k equals 1 to n of pi times h plus a k delta x And what you see here, this actually is, look at this summoned, look at this summoned. Well, b minus a over n right here, that is just delta x. This constant I can pull through so it won't affect anything. And then look what I've got. h of a plus k delta x, f of a plus k delta x. So at the end of the day, we know that this is going to equal the definite integral from a to b, times pi, here's my pi times the definite integral from a to b of, let's see, what does it say? Yep, this, I'm sorry, I'm going back and forth. We know this equals, right, the definite integral from a to b of f of x dx. That was like the big day, right? That's what we know. By definition, the limit of a Riemann sum equals this. Well, that means this equals pi times the definite integral from a to b of the integrand is h of x dx. But what was h of x? H of x was no other than this. Ta-da! That's it. That's all it is. Just playing with Riemann sums. I hope that answered your question. I thought that was actually quite fun. It's just remembering that when you take a function, the key is right here. When you take a function and square it, this is just another function. And to make this kind of resemble this from back in the day, we have to remember, like, oh, I can just create a new function called h of x. H of x is the kind of function squared function. And I have a right endpoint Riemann sum. And there you go. Bye.